Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, well, we're happy to have Dan Bow, who's here today. He returns after a few years. He was an intern on our team a few years ago, working with Tim Peck and I on some interesting problems that related to his own dissertation work. There's a big dream that if people and computers could interact the same way that people and people do when it comes to grounding and robustly handling errors, that even with less accurate speech recognition, we'd have a kind of a fluid user experience with dialogue systems. And Dan's been working in that space. Dan's a PhD student working under the supervision of Alex Rudnicki and Rennie Rosenfeld, and he's finishing up this coming spring working on adaptive techniques for error detection and recovery in spoken language interfaces. He developed a task-independent dialogue management system/framework called Ravenclaw that's served as a platform for several projects at CMU in a variety of domains. I actually was visiting about a year ago when I actually called up for some bus information in the middle of the street in Pittsburgh, and they didn't fail miserably, but it was interesting, I should say. Dan will speak today on belief updating in spoken language interfaces.
Right.
Dan.
There's errors to fix, yeah. So thanks a lot, Eric, for the intro. And actually, before I go on, Alex, I want to also acknowledge my advisor, Alex Rudnicki at CMU, and actually also Eric and Tim here at Microsoft Research, since some of the ideas that I'm going to talk about today stem from an initial internship that I did here in 2003. So spoken language interfaces. Well, these things have a great number of promises, right? They rely on natural language, so that means they require no or very little user training, which in turn opens them up to a very wide user population. Secondly, you can very easily construct complex queries using natural language, and that creates an opportunity for a very efficient interaction. Third, speech is an ambient rather than an attentional modality, which means it's appropriate in all sorts of situations like hands busy, eyes busy, and ultimately, right, it will play a key role in the quest for ubiquitous computing, building ambience intelligences, and so on. Now, these are some of the promises. Unfortunately, if we look at today's realities, they're better described by this kind of cartoon that I got from the Sunday paper, where the punchline is, as a final part of your stress test, you have to call an automated phone system. And I do think that one of the most important and persistent problems in these interfaces is the fact that they're still very, very brittle when confronted with these understanding errors, right? They still fail. And this observation forms the starting point for my research and for the talk that I'm going to give today. So let's take a closer look at these understanding errors. I argue that most of them, to a large extent today at least, stem from current limitations in speech recognition technology. Speech recognition is a difficult problem to begin with, but in the context of these systems, the problems are further exacerbated by the operating conditions. Right? Generally, these systems are targeted at large user populations. So you have to deal with a lot of variability in speaking style, accents, natives, non-natives. You have to deal with variability in the quality of the input lines. People call over cell phones, over regular phones, using voice over IP solutions. Now, if you add on top of that all the disfluencies that come with conversational speech, it's actually not surprising that recognition error rates are somewhere 50 and going up from there to 40% or even higher if you have any sort of extreme population or adverse noise conditions. And repeated studies have shown that these errors have a very strong negative impact on the overall quality and success of the interactions. The plot I have here shows probability of task success as a function of word error rate in a deployed application we have at CMU that handles conference room reservations. And as you can see in this 15 to 40% range, there's a very sharp drop in that probability. But I do want to still stay away from numbers and make these problems more concrete by actually showing you an example. This is a sample conversation with the CMU communicator, a dialog system we built a while ago at CMU that operates in the air travel planning domain. So you can call it up over the phone, and you can make flight reservations with multiple leg trips and hotels and cars and so on. I'm going to play this for you in a second, but before I do that, I want to tell you about the color encoding. So the system speech is in red, the user speech is in black, and following the user speech, in between brackets, we have the actual recognition results. The words in lowercase in the recognition results are tagged as unconfident by the speech recognizer, and in this system, they're ignored for language understanding purposes. Okay? So with that, I'm going to play this for you, and we'll see what kind of problems we get into.
What city are you leaving from?
Urbana-Champaign.
Sorry, I'm not sure I understood what you said. What city are you leaving from?
Urbana-Champaign.
I'm still having trouble understanding you. To go on, I need you to answer the following question. What city are you leaving from?
Chicago.
Traveling from Chicago. Where would you like to go?
Huntsville.
Traveling to Seoul. What day did you need to travel?
No, traveling to Birmingham.
Traveling in the afternoon. Okay, what day would you be departing Chicago?
The 10th of August.
A flight tomorrow. I have a Korean Airlines flight departing Chicago at 1:40 p.m. Arrives at Seoul at 5 p.m. the next day. Do you want to take that?
My destination is Birmingham.
Traveling on Saturday, August 12th. I have a flight departing Chicago at 1:40 p.m. Arrives at Seoul at 5:05 p.m.
Right, so my job in this talk is to get this poor soul off the flight to Seoul. Now, seriously speaking, this is not a corner case interaction. I didn't have to dig up too much to find one of these in the corpus that we have. And if you call these systems, you know the frustrations that you have with them. And there's a number of things that are going wrong here. So generally speaking, what can we do about this? Well, I think at a very high level, there's sort of two kinds of approaches. On one way, you can try and prevent the errors from happening altogether, right? And there's a lot of concerted effort going in that direction, right? Build better speech recognizer, build better spoken language understanding technologies. Now, a second approach would be to assume that, some errors will always be there and try and handle them through conversation by interacting with the user. Sort of how humans do it when they get into misunderstandings, okay? Now, clearly, these two approaches, they don't stand in opposition, and what you really want is a combined effort. In my work, I'm interested in the second problem especially. So I'm interested in how can we create the mechanisms that allow these systems to sort of gracefully and efficiently recover from errors through conversation. And I think if you choose to go down that path, there's basically three main ingredients that are needed. First, we need the ability to detect the errors, preferably as soon as they happen. Second, we need a rich set of error recovery strategies that the system might use to set the conversation back on track, right? So here, by error recovery strategy, I mean a simple one-step action, like asking you to repeat or asking you to rephrase or giving you some help or confirming a piece of information, right? The third component, which is just as important, is these systems need to be able to choose wisely between these strategies at runtime, right? When do I ask you to repeat versus when do I ask you to rephrase, right? So there's a control problem there. The third level, I call that the recovery policy, right? That's another problem. And I think this is a really, really interesting and exciting space, and there's a lot of really interesting and important problems in there, and they have different flavors also. At the detection level, you're mostly dealing with some sort of pattern recognition problem. At the recovery strategies level, it's more of a interaction design, HCI kind of problem, if you want, developing this set of strategies. And then finally, at the last level, we're faced with a problem of control under uncertainty. In my dissertation, I bring a number of contributions in each of these areas. But given the limited time that we have here today, I'm going to focus on one particular problem that lives at that level. It has to do with error detection. At the end of the talk, I'm going to come back to this high-level view and just briefly mention some of the other pieces of work that I've done to sort of give you a better sense of the scope of this research program. And in case any of you guys are interested in talking about any of the other issues, I'd be more than happy to. Okay? So for today's talk, we're going to focus on error detection. So let me introduce the problem by bringing back the example that we've seen before. And this time, I'm going to take away, so I'm actually taking away the user utterances. We get the exact same perspective that the system has, right? We see just the recognition results. Now, what do systems do to detect errors? Well, generally, they rely on the so-called confidence scores, right? The recognizer, apart from the recognition result, also gives you this score that tells you how much it really trusts that that's the correct recognition. Let me focus your attention on this term here, where the system says, traveling from Chicago, where would you like to go, right? The user responds something, we don't know what they said, but the recognizer produced Seoul and a confidence score of 0.65. Now, based on this confidence score, the system assembles an initial belief that the arrival city is Seoul with probability 0.65, right? And at this point, it has a number of choices. It has a number of potential options with respect to how to deal with that value. Typically, the action is decided based on the confidence score. So, for instance, if the confidence score was very, very low, the system might decide to reject that value altogether, pretending it never heard it. Because if the confidence score is very low, that's most likely a misunderstanding, right? Alternatively, the system might try to explicitly confirm it with a simple yes-no question. Did you say so, right? Another option would be an implicit confirmation, in which the system echoes back the value it heard to the user and then goes on with a conversation with the hope that if there's an error, the user will detect it, will catch it, and will interject a correction, right? Finally, if the confidence score was very, very high, the system might simply accept that value, consider it grounded, and just move on. So these are some of the options that it might have. Our system here did an implicit confirmation, right? So it echoes back this value to the user. It says, traveling to Seoul, what day did you need to travel? With the hope that if the value is incorrect, the users are going to make the correction. And that actually happened in the dialog. But unfortunately, the user response is also subject to recognition errors again, right? So we get this response, the traveling to Berlin PM, with a score of 0.35. Now, the question I'm going to address in today's talk is, what should we now believe about the arrival city, right? We started with that initial belief that it's Seoul with probability 0.65. We did this action, an implicit confirmation on that concept. We got a follow-up user response with a new confidence score. What should we believe about it now? How much should I trust it's Seoul? How much should I trust it's Berlin? How much should I trust it's anything else for that matter? Right? So that's the problem we're going to try and handle. So what I want to do is essentially construct this one-step belief updating function that takes an initial belief, takes a system action, and the follow-up user response, as this response is perceived by the system, and gives me an updated belief that's as accurate as possible. Okay? Now, if you look out there, it turns out most systems use very simple heuristics to do this belief updating. A very commonly encountered one is letting new values overwrite old values. Right? The idea is, if users are going to correct throughout the conversation, trusting the last thing I heard is a good thing. Right? But by the end of the talk, I hope I'll convince you that we can do much better than that. And really, the hope is here, if we can do this one-step belief update in an accurate fashion, then we can chain it throughout the conversation. Do it for all the concepts that the system operates with, and endow it with the mechanism, right, to constantly integrate evidence from multiple turns and constantly update the belief. Okay? The one-step problem is just this one, and you can formalize it as follows. Given an initial belief over a concept, in this example, Seoul with probability 0.65, a system action with respect to that concept, in this case, the implicit confirmation, and a user response, construct a belief that's as accurate as possible. Okay? Are there any questions at this point? Okay, so here's the outline for the rest of the talk. I'm going to start by describing some related work. Then I'm going to discuss the approach that we took towards solving this problem. After that, I'm going to switch gears a bit and talk about the experimental platform we used, the data we collected to build these models, and the results that we got. From there, I'll move on to discussing the effects of these belief updating models on global dialog performance. And then I'm going to conclude by summarizing this up, presenting a few ideas for future work in this line of research, and then going back to the big picture with the rest of the work in my dissertation. Okay? So let me start from related work. Well, it turns out most systems actually don't track beliefs. If you look out there, they don't track multiple alternate hypotheses at the concept level. Most systems store a single concept value and associate with it a confidence score, maybe a confidence indicator like low, medium, high, right? And base their actions on that. And then they use simple heuristic rules, like I described before, letting new values overwrite old values, to perform these updates. There's a few additional rules to deal with the confirmation cases. So, for instance, after an explicit confirmation, like did you say you wanted to fly to Seoul, the system might look for a yes-type answer, like yes, that's right, that's correct, and so on. And if he finds it, it's going to just trust that hypothesis. If he finds a no-type answer, then he's going to delete it altogether. But if the recognized user response doesn't fall into any of those categories, the system's going to be kind of stuck. It's going to have a non-understanding. The belief doesn't get updated. For implicit confirmation, again, the situation is not much better. A lot of systems engage in these actions, but they're not really able to handle sort of the wide spectrum of language responses. So, like, following implicit confirmations, user responses cover a broader language spectrum. That's difficult to deal with. And simply relying on this idea that new values will overwrite all values is insufficient. And we'll see that by the end of the talk. Now, while these are some of the common solutions, if you look out there in general, in research, the idea of updating beliefs throughout a conversation and fusing information across multiple turns appears before actually in work here by Eric and Tim Peck on the Deep Listener project. And Deep Listener is a system that operates in a relatively simple command and control domain, where the goal of the system is to identify one of 5 possible user intentions. This was designed as an interface to the Lookout project. I think, Eric, correct me if I'm wrong on any of this. So the goal is here is to identify what's the user intention, and those were the 5 intentions. And the system uses a handcrafted dynamic Bayesian net to fuse evidence across multiple turns and identify which one really is it, and then guide clarification dialogue based on that. Now, the work that I'm going to describe today is inspired actually by the Deep Listener work and stems from an earlier collaboration I had with Eric and Tim here during my internship, where we're looking at how can we scale up that model, to more complex applications where you're working with many different concepts that can have hundreds of possible values, right? The belief updating models that I'm going to describe today do have that good scalability properties. In fact, I'm going to show you experiments with a deployed spoken dialogue system of a large size. And then the other thing about them is the model parameters are induced from data. The model used a wide variety of features from different knowledge sources in the system to perform this belief updating, and the parameters are induced from data. So it's a machine learning solution. Okay? And with that, I'll move on to describe the actual approach. Right? Let me bring back the problem. The problem we're trying to solve is, given an initial belief over a concept, a system action, and a follow-up user response, we want to construct an updated belief in a manner as accurate as possible. So what I'm going to do over the next couple of slides is I'm going to take each of the terms in this equation and describe in a bit more detail how we represented them and then how we modeled the belief updating process. I'll start with the beliefs. So I've sort of thrown around this term belief, but I didn't really define it in any precise way. If you think about it, if you want to model, say, belief over a departure city in a flight reservation system, the most accurate way of doing it would be to store a probability distribution over the full set of possible values for that concept, right? So you line up your cities from Aberdeen, Texas to Yuma, Arizona, and you store this very large degree multinomial, right? And that represents your belief. Now the problem with that is that it renders intractable any sort of data-driven approach to building that, because of data sparsity issues, right, of building that belief updating function. There is, however, an observation that comes to the rescue, which is even though there are 5,000 different possible city names, let's say, the system is not going to hear all 5,000 of them throughout any given conversation, right? Because of the way speech recognition works, if you think about it, the system will hear maybe 1, 2, 3, 5 different conflicting values for what the city really is as the user tries to get the information through, but it's not going to hear 5,000 of them. And this intuition is actually confirmed by empirical evidence. We looked in a corpus of dialogues from this conference room reservation system, and for any given concept throughout any conversation, the system never heard more than 3 possible values, right? That's important because it opens up the opportunity for using a compressed representation of beliefs, right? And instead of keeping track of these 5,000 different city names, we're going to keep track just of the top k most likely ones, where k is going to be a really small integer like 2 or 3 or 5. And we're going to cluster the rest of the probability mass into this other category for all the other ones that are very low probability. Right? So for instance, a belief over a city name might look like that, where my top 3 most likely cities are Boston, Austin, and Houston, and all the other ones are clustered into this other category. Okay? Now once you decide to do that, there's a problem that comes up, which is, what if I hear more than k throughout the conversation, right? I'm prepared to handle k, right? But what if I hear more than that? So what I need is some ability to dynamically drop all hypotheses from this belief space and add new hypotheses in it as I hear them throughout the conversation. Okay? The way we're going to do that is out of the initial k hypothesis, in every belief updating step, out of the initial k, I'm going to remember m, the m most likely ones, and I'm going to add n new ones from the recognizer in each step so that m plus n give me k. I'm going to show you this with an example. It's best illustrated with an example. So say that's our initial belief. Say we're in the case k is 3, m is 2, n is 1, right? And in this case, Austin is the most likely hypothesis. So let's just assume the system does an explicit confirmation. It's trying to confirm that value. So it says, did you say you were flying from Austin, right? The user responds, but what we hear back is no, Aspen. At this point, I want to update my belief. So what I'm going to do is from the 3 initial hypotheses, I'm going to keep the top 2 most likely ones, since M is 2. Those are Boston and Austin. So I'm dropping Houston at this point. And I'm going to add 1 new hypothesis from the recognition result, which is Aspen. And I'm going to construct an updated belief over that space. Now, how exactly that histogram, that belief gets updated, I'm not discussing that yet. That's that belief updating function. I'll get to that in a second. Here, I just want to show you this representation where I can dynamically, throughout the conversation, add and drop hypotheses so that I constantly keep K at any given time. Now, Aspen is the new top hypothesis. So say I do an implicit confirmation, flying from Aspen, what is your destination? And the recognition result is that I get is, no, I didn't that. Well, again, I want to update my belief. So from that space, I'm going to retain the top 2 most likely ones, Boston and Aspen, right? And I'm going to add 1 new hypothesis from the recognition result. Unfortunately, my recognition result has no city hypothesis in it for that concept. And so I'm going to add this fictitious void hypothesis just to maintain consistency in the model. And I'm going to update my belief. Okay? Yes?
What does the void hypothesis mean that other doesn't mean?
It's basically the same. It's an artificial thing that the system has. It's as if this is going to be forced to be 0, essentially. It's just so that I can maintain a consistent model in this belief updating process, right? So it doesn't really mean anything. Like the system doesn't have a value for it. That doesn't.
So this is really forced because you're insisting on adding.
Exactly. Because I want to keep that. Invariant, if you want.
So
yeah. Because that's gonna help me later when I want to build that function.
Okay.
Right. Yeah. Yes.
So you determine which one to keep before you update.
Absolutely. Absolutely. Before even I hear the recognition result, I already know I'm keeping my top 2. In this particular model, I could choose a model with different parameters and keep more or less, but yes, they're determined before you even hear.
What's the reason to do that instead of updating the list after?
Again, I can get back to this question in a second. It has to do with maintaining a certain consistency in the model so that I can build that function. But I'll come back to it if it's not answered by the end, okay? So essentially what I'm doing is instead of modeling that belief as a multinomial of a very large degree, now I'm modeling it as a multinomial of degree k plus 1, where k is a small integer. And that's going to make my learning approach tractable on this problem. Then we move on to the second component here, which is the system action. We identify 4 types of actions that the system might engage in with respect to any given concept. Request is the first time the system asks for a value for a concept. So when would you like to take this flight is a request for the date concept, right? Explicit confirmation, did you say you wanted to fly this Friday? Implicit confirmation, a flight for Friday, at what time? Note that in any turn, the system might do multiple actions with respect to different concepts. So for instance, this particular system action here is a combination of an implicit confirmation on the date and a request for the time. When I'm going to update my beliefs, I'm going to pay attention to the action with respect to whatever concept I want to update. Okay? Finally, there's a 4th action that we introduce, the so-called no action or unexpected update case, which is best explained with an example. So imagine the system saying, would you like a hotel in San Francisco? And the user responds, I want to rent a car with Avis. Right? Now all of a sudden I have this car concept in my hands. I didn't try to request it explicitly or implicitly confirming. I didn't try to do anything about it, but all of a sudden it appears. So I want to update my belief. In this case, this happens because it's a mixed initiative system and the user can shift the conversation topic somewhere else. But this often happens also because of misunderstandings. Things are misunderstood as something else, right? And in order to handle this case, we introduce this 4th action type, which is called an unexpected update. 3rd component is the user response. We characterize the user response in terms of a large set of features from different knowledge sources in the system. There's about 270, almost 300 features. This is just a summary of them. We started from the acoustic level where we looked at acoustic and language model scores, duration of the utterance, various information about the pitch contours, so prosodical information, voice-to-voice ratio, how fast people were speaking, what's the length of the initial pause, all sorts, anything we could extract sort of from the acoustic level. Then we moved on to the lexical level where we're looking at the number of words and also whether there are words in the utterance that are highly correlated in general with acknowledgments or disconfirmations, right, corrections. From the grammar level, we look at number of slots or number of concepts in the parse and how many of them are new, how many of them are repeated compared to the previous utterance, right? Are people repeating themselves? Various goodness of parse scores. At the dialogue level, we look at information about what state the dialogue is in, what's the turn number, how well is what we heard from the recognizer matching what the system expects to hear from the user at this point, was there timeout, was there barging, what's the identity of the concept we're on, all sorts of other dialogue history information, all sorts of other information. And then we added two other classes of features, priors and confusability. The priors measure the prior likelihood of each individual concept value, right? So in a conference room reservation system, people are not going to make reservations starting at 11 p.m. So 11 p.m. is not really a good value for start time, and knowing that will prove helpful. Also confusability, Thursday and Friday are more confusable than Thursday and Monday. Well, that's good to know. So we used all these features, and then that brings me to the last component here, which is the actual belief updating function. Now, we've seen that we're modeling this belief as a multinomial variable of small degree. So essentially what we have in our hands here is a multinomial regression problem. And you can train a multinomial generalized linear model from data to solve this problem for you. This is essentially the extension of a logistic regression model to a multi-class problem, right? It has a number of good properties. It's sample efficient. It can be constructed in a stepwise approach. So you can do feature selection, right? Like in any regression, you can investigate this large pool of 300 features without necessarily knowing all the relationships between them, as you need to do if you wanted to build a more structured model. You can use Bayesian information criterion to control for overfitting. And one last point that I like to make here is that we built one separate model for each system action. So if initially I had the system action as one of the features or parameters in this model, we actually took it out and built one separate model for each system action. The rationale for that is the features in the user response will play different roles. They mean different things depending on the context of the action you're in. For instance, if there's a yes in the user response, that means something if I'm in the context of an explicit confirmation. It means something else if I'm in the context of a simple request, right? So we built one separate belief updating model for each of the 4 actions, okay? And with that, I'm going to, like I said, switch gears a bit and talk about the experimental platform, the data we gathered to build these models, and the results that we got. So the experimental platform consists of this Roomline system, which is a phone-based mixed initiative dialogue system I built at CMU that handles conference room reservations. The system is connected to a corporate Times server that has the live schedules of 13 rooms in 2 buildings on campus, and people on campus can call it to basically reserve rooms. The system is based on the Ravenclaw dialogue management framework, and I'm going to take just a short minute here as an aside, because this is another part of my research that actually today serves as infrastructure for all this work in error handling. But this is something I developed in the first 2-3 years during my stay at CMU. It's an open source. We've recently open sourced this dialogue management framework that has to date been used to build a number of different systems spanning different domains and interaction types. Some of these systems have been deployed into day-to-day use. Roomline is this conference room reservation system I just mentioned. Oops, sorry about that. Let's Go is a system that provides bus schedule information that Eric was talking about. This is actually connected to the Pittsburgh Port Authority bus line at night. So people call it like we get real users from the streets. There's like 30,000 calls accumulated in it so far. Finally, if you've been at Interspeech or HCI recently, you might have seen Conquest, which is a dialogue system that provides technical schedule information during conferences. Then there's a number of other systems in different domains. I'd be more than happy to talk about them if you're interested at the end of the talk. The point is that together with these systems, this dialogue management framework provides a robust basis for research in this area. And I'm using it personally for research in dialogue management and error handling, but there's a number of other projects at CMU and elsewhere that are using it, for instance, in investigating timing and turn-taking, issues in multi-participant dialogue, and so on. Again, if you're interested in that area of dialogue management and system building, I'd be more than happy to talk about that at the end if you have questions. So getting back to Roomline, right? So we use this system, we ran a user study with it to collect data to build these belief updating models. We had 46 participants interacting with the system. They're all first-time users, and each of them performed 10 scenario-based interactions with this system. We collected a corpus of 449 sessions, almost 9,000 user turns, which were orthographically transcribed, and then manually annotated with information about where were the misunderstandings, where were the user corrections, and what were the correct concept values at each point in the dialogue as the users were specifying them, right? So that's going to provide our training data. And with that, I'm going to move on to discuss the model training and the results that we got. Now, remember there's a parameter in this model which is k, which is how many hypotheses, the maximum number we're keeping. Yes?
Sorry, the sessions used for training, were those in a Wizard of Oz, like a human operator?
No. So it's an actual system that collected them. This is the deployed system. We just had them do scenario-based interactions. We wanted everyone to do the same task.
I see.
The scenarios were presented graphically. We did all these things, tried not to lexically train them. We also compensated them per task success, trying to motivate them. So it's basically a control in the lab experiment with a real system. Yeah. So there's that parameter k, right? Here I'm going to show you results for the model with k equals 2. So at any given point in time, the system keeps track of at most 2 hypotheses and clusters everything else into this other category. I build models for larger values of k up to 4, but there's no statistically significant improvements over this simple one. So I'm going to stick to this simple one. We also investigate different subsets of the features to try and, we did many more. Here I'm showing you 2 models. We're trying to tease apart which features play a more important role. So here I'm going to show you 2 models, a model that uses all the features except for priors and confusability information, and the full model that uses the full feature set. And then I'm going to compare the performance of those models against 3 different baselines, initial, heuristic, and correction. I'm going to describe those as we go along as I show you the results. Okay? Now, one last thing. Remember there's 4 actions, right? And we built one separate belief updating model for each of the 4 actions, request, explicit, implicit, and the no action case. I'm going to start by showing you results for the explicit confirm case. They're sort of easy to understand. So in the case of explicit confirmation, the numbers I'm going to show you represent error rates. So they reflect the error in the constructed belief. Okay, so lower is better. The initial baseline reflects the error in the belief on average before the system engages in the action. So right here at this point, before I'm doing any belief update, on average, how much error do I have in my belief? And whenever the action that follows is an explicit confirmation, that's 30%. That basically says that in this system, in 30% of the cases when the system was trying to explicitly confirm a piece of information, a value, that value was incorrect. Okay? The second baseline is the heuristic baseline. And this shows the error in the belief once I update my belief using the simple heuristic rules that the system uses that I described before, right? This kind of letting new values overwrite all values and looking for simple yes, no after explicit confirmations. So that drops. So that's good. That's what you want. Now, it doesn't go to 0, but it drops. The third baseline is something I call a correction baseline. I'll explain this. So the idea here is imagine you had access to the transcript here. Imagine you could peek at what people actually said. Imagine you have a perfect recognizer in the next turn. It turns out that even if you had that, you wouldn't be able to perfectly construct a perfectly accurate belief in one step, because people don't always immediately correct. Someone here might say help or something else. So I still am not clear if Sol is right or not. So I have this residual error of 6.2. So what I really want to do with these models is beat that heuristic and get as close as possible to that correction baseline. Yeah.
So I can understand. So you basically transcribed actually what the people really said rather than using the repertoire, but then trained up a model based on that.
Not use the heuristic in connection with the transcript.
Use the heuristic in
connection with the transcript. Right.
Okay.
So, right. Exactly.
But you could have actually made
Oh yeah, I could have. But that's, I mean, obviously the ultimate goal here is to get to 0, right?
Right.
But I mean, so training based on the transcript doesn't, right? Like you can use that in any way live as a comparison, I guess.
We can't
getting
use
to
heuristic
0
live either. On the
right. Sure. I guess. Yeah. Right. So, anyways, so the models do that. The basic model, both the basic and the full model, beat the heuristic. And more interestingly, actually the full model beats the correction baseline. And at this point you might say, well, how is that possible? The reason that's possible is because these models, the full model uses high-level knowledge like priors, concept identity. So knowing, for instance, like even before the user responds, the system gets a sense that something is fishy and adjusts that belief better. And information like priors, confusability, barging, which is not present even if you have the transcript, you don't know that they barged in, right? So that kind of information can lead you to build somewhat better beliefs. Then for the implicit confirmation case, it looks like this. The initial is again around 30. The correction is much higher at this point. And this is actually consistent with observations we've made and others have made, that especially after implicit confirmations, people are not always going to correct immediately. They're going to let them go by a lot of times. The heuristic closes about half this gap between the initial and the correction. Both models here significantly outperform the correction baseline. Again, with the models that uses prior information doing better. For the request case, remember this is the case when the system first asks a value for the concept. Here the initial baseline sort of loses its meaning, right? Obviously, before I ask you for what the value is, there's no way I can have the right belief, right? However, it's interesting to look at the pattern between the heuristic, the basic, and the full model. The heuristic, what it does is it just takes whatever comes from the recognition result with a confidence score, right? And trusts that confidence score. The fact that our basic model doesn't do much better says that that heuristic is already, that confidence annotator is pretty well calibrated in that domain. We cannot improve it much by throwing yet another, thing on top of it. However, once we add information, priors, and confusability, which the confidence annotation model does not know about, we do get another improvement in the belief. Similar picture for the no action case, where both the basic and the full model significantly outperform the simple heuristic. And again, throughout all this, you can see that generally the full model, priors and confusability, high-level knowledge matters a lot. Okay? So what I've shown you so far is that we can use this data-driven approach to build in one step beliefs that are more accurate, significantly more accurate than those constructed by current heuristics, right? There's one question that remains. Does this really matter? What we're after actually here, we're not just after, constructing accurate belief. I've shown you an improvement, from 15.2 to 6.8. What does that mean, right? What I'm after is good dialogues. I want happy users. I want fast conversations, high task success. So we decided to explore the effects of this model on global dialogue performance. So we ran a second user study, which was run as a controlled experiment with two groups, two gender balanced groups. Participants in the control condition interacted with the old system. Participants in the treatment condition interacting with a system that was identical in all respects except that it used the new belief updating models. Okay? This time we focused our attention on non-native users. The reason for that was as follows. At low word error rates, if you recognize the works perfectly, you don't really need to do any of these tricks, right? You just trust you recognize everything will work well. There's no space for improvement. However, as word error rate degrades, right, as you have more and more problems, it becomes more and more important to do this game and sort of model these beliefs through time and update them. Now, I should say that even though we did that, the average per user word error rate in this experiment ranged from as low as 4% to as high as 60%. So we covered a very wide range. And my personal lesson from that is that you have to be really careful how you word your ads, because a lot of bilinguals on campus will happily declare themselves non-natives to get $25. So in light of that, but anyways, that was my lesson. Each of these people, again, were first-time users. They performed 10 scenario-driven interactions with the system. The first thing we look at was task success. Are people more successful with the new system? And it turns out they are. In the old system, probability of the average task success rate is 73.7. It goes up to 81.3. Now, if you do a simple statistical comparison of these numbers, the p-value comes at 0.0724. So that's a bit disappointing, but there's a really important factor we must not forget in here. There's a confound, which is the word error rate. A lot of the variance in each of these groups, both the control and the treatment condition, is explained by the internal variance in terms of word error rate. Some people had stronger accents than others. So if you add that factor, you can do a more powerful, more sensitive statistical analysis, which teases that apart. So we did this logistic analysis of variance on task success, where the main effect was the experimental condition, and we added in the average word error rate as a random effect, right? And this shows that the condition has a statistically significant impact on the probability of task success. The p-value is 0.009, and the impact is described by this curve here. This is a curve I showed you at the beginning. It's basically the probability of task success as a function of word error rate in the old system. In the new system, it looks more like that. Indeed, as we expected, we get larger improvements at larger word error rates. So for instance, if your word error rate is about 30% on average, then you improve from 64% to 78% in task success. Another way to look at that is to get the same performance with the old system, you'd need a word error rate of about 16%. So in effect, these models create an improvement that's equivalent to a 14% absolute reduction in word error rate in this case, or a 50% at this particular point relative reduction in word error. So that was a nice result, I thought. And the next thing we look at was duration. Okay, so people are getting more things done. Can they get them done faster? Again, an analysis of variance on task duration for successful tasks shows that the experimental conditioner has a statistically significant impact. The impact is negative, so people get things done faster, and the improvement is significantly equivalent to a 7.9% absolute reduction in word error. Okay? Now, apart from sort of these improvements in effectiveness and efficiency, there's a number of good properties for this model. First of all, they're induced from data. They're learned, so they're really tuned to the domain in which the system operates. Secondly, the models are actually sample efficient and scalable. I have an analysis of that, and I can talk about it. The key point is we're making a local one-term optimization, and we're also working independently. We're treating each concept independently. And while those might seem like sort of big assumptions to make in the world of dialogue, for error handling, a lot of times it turns out that your problems are mostly local, or at least if you're able to do good locally, those things will sum up and you'll do good generally. Finally, the approach is portable. It's decoupled from any dialog task specification, so you can use it in any dialog system. It makes no strong assumption about the underlying dialog management technology. It doesn't tie you in any type of controller, like a reinforcement learning approach or something like that might do. As long as you have a notion of concept that you can update, throughout the conversation, you can play this game. And with that, I'm heading towards the summary. So what I've shown you here is an approach for constructing more accurate beliefs that integrates information across multiple turns in a conversation and produces large gains in both task success and efficiency in a real-world deployed application. There's a number of future directions that we can take this, and I'm actually collaborating with Tim on a number of these issues, trying this out on another data set we collected during my initial internship here at Microsoft. One idea is to integrate information from an M-best list. So the models that I've shown you so far use the value of N1. So in each turn, I grab one new hypothesis from my recognizer. But there's no reason why I couldn't grab 2 or 3. Right? If my recognizer produced an M-best list, I could grab in each turn 3 and juggle all those through time. Another question is domain specificity. We're trying it in a different domain. Other ideas are integrating other high-level knowledge. We've seen the importance of priors, concept identity, general high-level features. Other information such as inter-concept dependencies and domain-specific constraints. People don't reserve rooms from 4 p.m. to 2 p.m., right? They reserve it from 2 p.m. to 4 p.m. So if I capture that constraint with a feature, it's a high-level domain-specific constraint, but if I can capture it, that might lead to further improvements in this. Also, ultimately, the approach that I talk about today is a machine learning solution, but it's supervised learning. So you need to label this data to build these models. And I'm looking at ways of doing this in an implicitly supervised fashion where the system gets its supervision directly from the interaction instead of from a developer. And with that, I'm going to come back to the big picture. So as I said before, the goal in my dissertation is to create the mechanism, in the research program, is to create the mechanisms for handling errors through conversation. I've argued that there's sort of 3 important components. There's the detection part, there's the set of recovery strategies, and there's the control policy. In today's talk, I focus mostly on the detection part. But in my work, I've addressed a number of these other issues, and I can just very briefly mention some of them in case someone is interested in talking to me about that. I don't know how we're doing on time. Are we still? Oh, we're fine. Okay. So the belief updating work that I described today actually also rests on previous work I've done on confidence annotation, which is just the turn level problem. And here my contributions have been, on one hand, just looking at integrating multiple knowledge sources in the system to build these semantic confidence annotators. But more importantly, what I'm more excited about is this implicitly supervised approach for learning confidence annotation models, where you don't need any supervision from a system developer. The system gets its supervision automatically from the user through certain error correction patterns that occur naturally in the interaction. Another problem I look here is error cost assessment. Detecting an error is one thing, but knowing how much you're going to have to pay for it is also really important in making any decisions. So here, a lot of times in the literature, you hear, like rules of thumb, like, false acceptances are twice more costly than false rejections. The intuition that I started from is that really we don't know what those trade-offs are, and those trade-offs might be state and system specific. So I propose a data-driven error cost assessment model by which we can infer these costs directly from data and then use them to optimize different trade-offs in the system, like for instance rejection thresholds, in a state-specific manner. But the recovery strategies, like I said before, mostly dealing with more of an interaction design, HCI kind of problem. How can we design these strategies so that they don't frustrate the users? And how can we understand sort of the spectrum of user responses and what happens after each of them? Here there's two types of strategies reflecting the two types of errors that we have. Misunderstandings, which are situations in which the system gets the wrong information, and non-understandings, which are situations where the system gets no information, right? So I've looked at strategies for misunderstandings, which are these explicit and implicit confirmations, and I've done a user response analysis trying to understand how users behave following these strategies. On the other line, there's many more possible strategies you could use to recover. You could ask someone to repeat, to rephrase, you could give them help, you can repeat the prompt, you can just say you didn't catch it, and so on. So I've investigated a large set of these strategies, 10 of them. And again, I've done a user response analysis in an effort to corroborate previous work in terms of understanding how users respond to these strategies and which responses are more likely to lead to successful recoveries. Finally, at the last level, the policy level, here we're facing with a control problem. And recently I've developed an online supervised learning method for building recovery policies in these systems. And the idea here is that you want to learn for each strategy how likely it is to succeed throughout the interaction, and also control for an exploration-exploitation trade-off to be able to do this online. And we've done experiments with this deployed bus information system. We've seen there was a gain there where the system learned in a period of 10 days how to better recover from errors. All in all, this is based on the Ravenclaw dialog management infrastructure that I've developed in the first part of my PhD, and on the systems that have been developed with it. And I guess I'll leave it at that and say thank you and open it up for more questions. Yes?
So you didn't modify the recognizer at all, right?
In this experiment, no.
And you mentioned that one of the features that you used was priors.
Right.
So what would happen if, in addition to using knowledge that reserving conference rooms at night is unlikely, you were to pass that information to the recognizer?
I'm a huge fan of that. I think like our systems. So as I said before, the way I've been looking at it is you can work on preventing the errors, or you can work on once they happen recovering from them. My work has mostly been on the second side. I'm a huge fan of that. I think in our systems, like the pipeline that goes from the recognizer to the language understanding to the dialog manager is very thin, and there's no information flowing backwards. That should definitely be done.
So that would help. But
right.
The other concern is it could be that all that you're doing here is just covering for mismatches between priors in both cases, for example, so that if you were to do that,
then this might not.
That you will get that much gain by doing this.
It's an interesting question that would be worth exploring, I think. Yeah. I mean, I can't say off the top of my head. You know, the idea is. There's certain types of information that we can fit. There's a problem with fitting information in the recognizer, right? There's certain types of constraints and information that we can easily put in the recognizers and others that we cannot. This type of model sort of works in a different kind of paradigm. So it might be able to compensate for whatever we cannot fit in the recognizer. But it's a good point.
So the other question is, what are the top features that you found?
Right. So I mean, I can show you an actual model, but I guess I can just tell you. So priors confusability help, concept identity, right? The system figures out that certain things get misrecognized more often than other. And then there's a flurry of all sorts of other features, right? If you look in the different models, starting from like dialog state information, which I guess that will also go easily into recognizer, lexical items like the presence of small, because small is often confused with no, you know, things like that. So they sort of, you see in the model. So the way the models are built is a stepwise approach. So you can look at the model afterwards. You can see how many features got selected. On average, these models have on the order of 10 to 20 features. And while stuff, like I said, high-level priors, all this stuff comes in often, you see every now and then features from all over the place, like from all sorts of knowledge sources. So, yeah.
So did you ever, I mean, I guess it would get more complicated, but if you updated more than one turn, or kept your history over more than one turn, so I mean, You haven't gotten to zero error.
Right.
So for those errors that you
right, if
sorry,
that
benefit,
that's an
like
interesting
keeping it
thought.
going, or do you introduce more errors?
Right. No, that's an interesting thought, and you might be able to build something that does better. There is an inherent problem in here, which is why I also did the second evaluation to make sure that these things really work, which is when you're training, your data is collected with a certain belief updating heuristic or whatever policy you previously have, right? And once you learn a policy and you put it, the whole behavior changes. So it's not clear that the basis on which you train will be the same as the basis which you're going to see at runtime. And I feel that if you chain more, that's even more likely maybe to hurt you more. It's not clear, but it's something that, yeah, that's an interesting idea. There was a question there.
Sorry, yeah. I've got two questions.
Sure.
So one is going back to this business of keeping M plus N hypotheses rather than just keeping the K best.
Right.
And it seems to me that really makes things a lot more complicated to have other and then zero, because then you could actually start to have several zeros.
Right.
Why not just keep the K best?
So let me explain this better. Let me see if I can get to a slide here quickly. Right. So what happens, because I want to cast this as a multinomial regression task, right? The way it actually works, right? So I have Boston, Austin, Houston, other. I'm going to define, this is my I1, my initial one hypothesis. This is my I2 hypothesis, right? And this is my N1, my new hypothesis, right? So what I need to be able to construct a model over the space I1, I2, new, and other. And that's, it's a constraint that needs to be imposed. I don't see how I can do it. You know, like my multinomial, this is a multinomial variable. It's one of these guys, which has probability I1, I2, new, other. These numbers sum up to 1. That's a multinomial variable. And that's my regression output. And I don't see, like, this needs to always be a 4-degree, like a degree 4 multinomial.
I see. So you're saying, unless you went to something like a Dirichlet process or something which has which generalizes beyond multinomials.
Right. So if you could generalize, right. So right, exactly. So this is a constraint that's imposed by the multinomial form of the problem.
Right. Yeah. Because then what I was thinking of, what happens? You showed before that sometimes you'd actually just, if you couldn't find a confident new hypothesis to introduce, you'd introduce a zero.
Right.
I mean, then you could have a zero. Then
those
one
zeros,
of those old hypotheses.
Those
is
zeros.
A zero.
So those zeros are forced their probability to be 0. Right. The probability of those zeros is forced to be 0. It's essentially transferred into other. So I'm never going to drop the other ones that I already have. I'm not going to drop them again. Right. The 0 always gets dropped. The void always gets dropped in the next.
Oh, I see. And
right.
So in other
so
words,
it's
if
not
those numbers
right.
are correct,
Right.
then you ensure that the zero. I get it. Right. Okay.
Yeah.
Second thing is actually picking up on the earlier question.
Yeah.
I mean, it seems to me that it would be. This is a higher level point. It seems to me it would actually be useful to remember that you'd gone through a disconfirmation.
I do that with features. I actually have features, and that's another feature that comes up.
So
have I already disconfirmed this?
But it's a pretty high-level feature,
yes,
then, right?
Yes, so it's a feature that's used in the model. We also use, so going back to Mike's question, we also use other features that describe the dialog history. So I have, for instance, how many previous non-understandings did I have in a row? What's the average confidence score so far? You know, things like that sort of describe the dialog history. Right. So there are features like that, but the model is not structured like that.
Right.
Yes?
Yeah, so your data seems to imply that if task accuracy is the ultimate objective, that using explicit confirmations is more reliable than using implicit ones.
Does it?
So I saw that you had an error rate associated with the confirmations in your slide deck, and it seemed that the implicit confirmation error rate was about double that of the...
No, they're the same. Oh, you mean following? Oh, right, following the implicit confirmation. That's correct. Right. Okay, you're correct. Okay.
So why rely on implicit confirmation?
Well, so there's a trade-off, right? So explicit and implicit, right? There's a trade-off. With an explicit confirmation, you're taking an extra turn out of the dialogue. In an implicit, if everything goes well, if the value is correct, right, then you haven't lost this time, right? This is like a trade-off between these strategies. On an explicit, you take an extra turn, so you pay a cost, but you're better off understanding what's going to come after it. In an implicit, you don't pay this cost, but you run a higher risk, right, of not understanding exactly what comes after it. So you just have to play this trade-off game, and there are methods for adjusting those thresholds of when do you do each, right? Ultimately, if you build a system that did always explicit confirmations, it can get very frustrating to a user also, right? Always, like engaging in this. So that's from more of an interaction design perspective. But there is this clear trade-off between these strategies where the implicit confirmation does not have this added one turn lost in the dialogue cause, right? Does that make some sense, or?
Yeah.
Okay. Yes.
I want to ask a little bit about this top-end assumption.
Right.
Can you reflect a little bit about, try to take a more fundamental view of probability theory and machine learning, and reflect a little bit about what the top-end constraint for all the tractability and computational savings you might get. What kind of problems you might have with that in terms of, for example, the stability of the learning problem to slight changes in performance and dialogue strategy, for example, as well as recognition performance.
Right. Right. So it's a good question. I haven't sort of analyzed this sort of from a theoretical standpoint and trying to look at it. I think my feeling is, so first of all, this is something that's appropriate when you're dealing with sort of multinomial type probabilities. Like if you have, continuous variables and other things, you don't have to worry about this. Secondly, it's also the structure of the problem. The fact that in the recognition...
Stop there, about that or not. With top end, I would think that you always have this issue of pushing some of the problem into other.
Right.
A lot
right.
of it that's not being represented explicitly.
That's what.
Distribution, no matter what you do.
Absolutely. So that's what I was going to say. Here we're getting a lot of traction. So that's a problem. I agree with you. And here we're getting a lot of traction from the fact that the nature of the recognition process and of dialogue, I don't hear too many of these, right? So I don't get hurt badly by that in this particular context. But I'm sure there are going to be other contexts.
By that, are you saying that the top end usually has a large degree of probability mass?
My feeling is
if you had a long, vibrating, unstable tail, right, you'd think that you'd be losing a lot by not representing it.
Absolutely. No, I agree with that. I agree with that. And I think in this particular problem, that doesn't happen so much, or the amount we're losing, the amount it hurts us is relatively small.
Because a lot of the mass is in the top end.
Right. Now, there are cases in which, in reality, there might be the case that the actual true value, so going into how recognition works, right, if you think about this particular problem, if there's an OOV, for instance, if someone says Urbana-Champaign, and that's not in my dictionary, in my recognizer for some reason, right, but it's in my tail, right, that's where the truth is. But I'm never going to model it, but I'm never going to get it anyway from the recognizer. So I can only play with the things that I hear from the recognizer. The space has 5,000, but I can only play with the things that I hear, and since those are just these few, right? I agree with you in general.
My high-level comment is, and I think I've had this in the back of my mind since we talked about this top end, is that it sounds like a useful heuristic,
right?
But I think there's some technical work to be done, kind of like in the UAI machine learning community, on what this really means per domain, and maybe we can make some
properties about, try and put some bounds or try and understand. Right, absolutely, yeah.
Well, if there's only 5,000 outcomes, why not just model all 5,000? Right? I mean, it's not a huge.
It's a huge degree multinomial there, right? I mean,
5,000 outcomes is not
for
that
multinomial.
big.
Well, maybe for the data that you guys have, but I have 400 dialogues. I mean, for building a data-driven model.
But the features have to be independent of the particular outcomes anyway, right? I mean, a lot of the features are things like, I saw this same thing. You're already doing a terrific amount of parameter tying.
All right, so this is an abstraction, right? So this is a compressed abstraction. So the features are with respect to that abstraction, is what you're saying.
And what I'm saying is that it's not going to be you're not going to have any generalization problems like that.
You're saying that I'm not going to have them if this was a 5,000 degree thing?
Yeah, I don't think so. I mean, because presumably the P other is collapsing all of the other alternatives.
Let
right?
me just.
So if you're doing that calculation correctly,
Well, the problem is the multinomial variable, the number of parameters in the multinomial variable, if I can find it. Right? So the number of variables in this model, right? They're these alphas.
Sure.
Right? And they're indexed by how many output classes I have.
But you've got to be considering all of those output classes anyway, right? I mean, there's some new thing that's being proposed, right, at each stage.
Okay.
So presumably what makes all of that tractable is that you're doing a certain amount of parameter tying. So I'm suggesting you still do the same parameter tying here. So
I'm doing, I'm not sure, maybe we can take it offline. I want to understand what you're saying, but I'm not sure I'm following. Like, or I'm sorry, can we talk here offline? Okay, thanks.
So you mentioned the formula that you have for updating the belief, right? But I haven't, maybe I missed it, I didn't see what is the formula that you use to figure out the next system action.
Right, so in this work I'm not talking about that. So in this talk the system action, the policy is fixed. Like it's some threshold based on the confidence score. You know, if my confidence is...
You write a state machine kind of thing and it can go here.
In some sense, yeah, you can look at it that way. I've done a fair amount of work on optimizing those thresholds. So that decide, you know, optimizing those trade-offs, right? So for instance, you might have a threshold that says, if it's below that threshold, if the confidence of the top hypothesis is below 0.3, reject it. If it's between 0.3 and 0.5, explicitly confirm it, you know.
But this is at an atomic
right.
Level, but how do you build a dialog system?
Right, so with respect to the error handling, so if your question is with respect to the error handling, what happens is...
Overall, how do you build a dialog system?
So that's the whole dialog management framework. That sort of, the one feature of it is, so you describe the dialogue in terms of a plan for the interaction, which is the domain-specific aspects of dialogue. Like first I have to ask you for the start time, then for the end time, then for whatever. And then underneath, Ravenclaw does for you the error handling automatically. So it automatically triggers these explicit confirmations or implicit confirmations at the right time. So you as a system author don't have to worry about that. Those things sort of happen magically by the engine looks at these beliefs that are constructed, right? And based on what the confidence score is and its current policy, decides which action to engage in. And if the engine decides everything is grounded, we're fine to go on, then the task just advances according to the plan that you specified.
So I guess the other question is, what is the relationship of your work with partially observable Markov process that maybe can jump around?
Right. So
there is a relationship.
So there's a good question there. There's a relationship. So there is like working POMDPs, right? POMDPs do belief updating in some sense. The problem with POMDPs, in the way I look at it, is that they don't scale well. And I think the part of the problem comes from the fact that once you get into this trying to model very large sets of possible values without some sort of abstraction of one form or another, right, or without some sort of compression, you just cannot solve that problem. People have done work with this with toy systems, with one slot with 5 possible values, and even then they have to use large amounts of simulation, like 100,000 dialogues to build a model. There's work by Jason Williams, which is really interesting, where he uses a compressed representation also in the POMDP world. And he shows some results, but then again, they're all like in user simulation, done with like hundreds of simulations.
One advantage of this, despite the computational, is that you could jump around. Like maybe you thought that the person was talking about a departure city, and you go asking, and realize that it's talking about a time or something else.
Right.
And you can escape.
Right. I agree with you.
Otherwise you get
I agree with
stuck.
you. I think it's just
that
not...
interferes with the policy.
Absolutely. So I agree with you, and I think it would be interesting here to look at those problems and building on top. My feeling is, rather than sort of looking, it seems like approaches like reinforcement learning POMDP that have looked at the problem in a global sense and have tried to cast the whole problem, in one nice theoretical framework, where it's sort of very appealing. They do inevitably seem to get stuck, or at least so far, into these tractability issues, and you cannot really deploy them or apply them, right? Unless you come up, there must be a way to come up probably with a smart abstraction or with compressed methods or something like that. In my work, sort of the philosophy has been more like, I'm going to try and look at my errors locally and fix them locally. And I agree with you that I'm sacrificing some of these sort of interdependencies in the process. But at the same time, I am getting gains that are quite significant just by doing this locally playing with things. I agree with you, like it is sacrificing that. Yes.
So when you're actually applying this model, you're basically, so you have like a little mini regressor for each output.
For
you can think of,
right, you can think of it that way, yeah.
As the whole,
right.
But your inputs are changing, right? Like,
Absolutely.
you know, I mean, as you go from, you get a new thing, some of your slots get replaced and so forth. So how do you choose the assignment of what?
Right. So that's
right.
So that's this abstraction here. So when I said I have k, right?
Okay, they're ordered k.
They're k, and so it's like I'm taking 1 and 2 because m is 2, right?
Okay.
I1, I2, and nu, and it's always that. Whatever this value is, whatever that value is, whatever the values are tracked.
So
separately.
the slot's meaningful. So like,
right.
It's whatever slot you're in. That's the
exactly. So it's an abstraction basically. Yes.
I'd like to know how sensitive you believe of the system with respect to the confidence of the definition. What is the next if I don't give you confidence at all?
Right. Give me a second, because I'm trying to think. I mean, the answer that comes off the top of my head is yes, I should be able, because these models, in some sense, they just do confidence annotation. Confidence, I'm using the confidence score of the incoming hypothesis as a feature, but I could throw it out, right? And actually, from my recollection, it does. So it does come in, but I don't think it's one of these things that would otherwise, because ultimately my confidence annotator also is built on the same type of features. So I'm using all the same features again, like acoustic features, right? All this different information. So this thing should be working even without a confidence annotator. Not off the top of my head, but I think it fully compensates for it. That would be my guess, because it uses the same set of features and it's trained from the same type of data. Yeah.
One more question.
Sure.
So, like you said, I mean, these probabilities, the first time they were getting generated by some heuristic measure, and then you have a new model.
Right.
And then potentially after you run a new user study with your new model, you're going to get different probabilities,
Absolutely.
which you would then need to
Absolutely.
maybe retrain. So
Absolutely.
do you have any idea what the...
That's why you want an online approach, where you get your supervision directly from the interaction.
So, okay, so do you
So
have
this
any
is
idea?
what I did do for the confidence annotation, but not for this, is this implicitly supervised approach, where the idea is, here I need supervision. I need some sort of signal that tells me, oh, I3 is the right thing, right? And the way I've done that, I've manually labeled based on it, right? With implicit supervision, what I do, I get that from the interaction, from, let's say, explicit confirmation. This will sound sort of counter to this work in some sense, because so let's say you say something, right? And I say, did you say Pittsburgh? And then you say yes, or I hear yes. I can take that yes as a label, and I can just believe it. Let's say if I hear yes with a high confidence score or no with a high confidence score, then that's a label that comes through the interaction. It's not going to be perfect precision. It's going to have low recall, right? All that. But you can get it through interaction, and then you can start thinking about doing this approach online, where the system sort of, as it goes, it continuously. And in my head, that's the solution to that problem, is sort of doing it online. Here, what I did to really validate the results is I did the post-experiment where I showed that, But now if I collect data with a new system and train it again, I might get another small bump,
Thanks very much for this.
Thank you. Thanks.